So you see a car ad, right? And it's boasting, I don't know, 40 miles per gallon.
Yeah, but that's on a closed track.
Exactly, that pristine test track number. But then you're grinding through city traffic, the AC is blasting, and, well, that's your actual mileage.
Right, a totally different reality.
And today we're applying that exact tension to evaluating systems. Welcome to today's deep dive, where we're looking at the fundamental gap between what a process can do in theory versus what it, actually does in practice.
And that gap is exactly why engineers have to split their evaluations into two distinct phases. I mean, if you're trying to figure out how good a manufacturing or quality control process truly is, looking at a single dashboard number just isn't going to cut it.
Because it hides all the context,
Right, you have to isolate the conditions. So first up, you have the peak performance study.
which is our pristine test track.
Exactly. You lock down all the variables, run it over a super short time frame, and just weed out all the random hiccups. You're only looking at the inherent variation.
You have the common causes.
Yeah, the common causes. It's the system operating at its absolute, perfectly stable best.
But, I mean, we don't live on the test track.
Yeah, we definitely do.
Yeah.
So to understand the day-to-day survival of a process, you run a process characterization study.
And that spans a much longer period, right?
Yes, and it captures everything, the inherent variation plus those special causes, like an operator making a mistake or a
Wow.
machine overheating.
Or a bad batch of raw materials coming in.
Exactly. And if you plot that out on a histogram, an unstable process doesn't give you a neat, pretty bell curve.
That's a total
A
mess.
jagged, unpredictable mess. You get weird spikes, flat spots. It physically maps the shape of your reality and all those real-world glitches.
Hey, hang on, though. I have to ask, if that peak performance study is just this, controlled fantasy, why are we even spending money and time on it?
Well, it's tempting to think that way.
Like, shouldn't I just focus my energy on fixing the messy reality?
It's really easy to just jump straight into fighting the daily fires. But you can't improve a process if you don't know its actual ceiling. A peak performance study establishes your baseline potential.
Oh, so you have to know what perfect looks like first.
Yes, you absolutely have to achieve statistical control first, meaning you've isolated and eliminated those unpredictable special causes. If your system is just constantly reacting to random glitches all day, you literally cannot reliably measure the underlying machinery.
Okay, so stability comes first, but let's say I'm a manager looking at my operations. I don't want a philosophy lesson on stability. I need a score.
Right. You want to see how you're doing.
Yeah, how do we actually measure that gap between the test track and the commute?
That's where capability indices come into play, specifically CP and CPK. They turn that whole conceptual gap into hard numbers.
Okay, break those down for me.
So CREEP scores your raw potential. It looks at the spread of your process compared to your allowable tolerance limits. But it makes one huge assumption.
Which is?
It assumes your process is perfectly centered on your target.
Oh, okay. So it's like your potential to hit the bullseye during quiet, solitary dart practice. You have this really tight grouping. You just need to aim straight.
Exactly. But CPK, that's where your darts actually land during a loud, crowded tournament.
When your arm is tired and your aim starts drifting to the left.
Yes, that drift is the key. Processes almost never stay perfectly centered over time. Tooling wears down, temperatures shift.
Right.
CPK accounts for that drift away from the target. It represents basically the worst-case scenario of how close your process is to failing specifications entirely.
So if you're perfectly centered, CPP and CPK are identical.
Right.
But the second your average shifts off that center point, your CPK just plummets.
Exactly. And here is the crucial takeaway for you listening, whether you're evaluating external suppliers or streamlining your own internal workflows. Performing these calculations on an unstable, out-of-control process is a fatal business error.
Because the numbers will lie to you.
Yes. If you run predictive math on a jagged, unpredictable mess, it might tell you you're capable when you're actually on the verge of a catastrophic defect rate. Stability must always precede capability.
Wow. So you need the peak performance study to find your stable baseline and the characterization study to reveal your actual drifting reality.
You map the potential with CP, and you ground it in reality with CPK.
But all of this relies on one massive assumption, doesn't it?
It does. For any of these predictive calculations to mean anything, the underlying data is supposed to follow a perfect normal distribution, a flawless bell curve.
Which leaves you with this to ponder. What happens to all those precise capability metrics when human behavior, which, rarely follows a perfect predictable bell curve, is the primary driver of your system's variation?
That's the real question.
If your daily city traffic is full of unpredictable human drivers, maybe that pristine test track rating isn't just optimistic, maybe it's entirely the wrong math to trust.